Hello students, welcome back. Previously we completed section 4, the Chinese remainder theorem. Now let's go to section 5, on application of Chinese remainder theorem in modern day computing. Due to the Chinese remainder theorem, any integer can be written as a linear combination like this, given moduli m1, m2, m3, and so on, which are pairwise relatively prime. Do you recognize this from the Chinese remainder theorem? If you do, great. In case you don't, let's go back to section 4 and have a review. The Chinese remainder theorem goes like this. We begin with this system of linear congruences with moduli m1, m2, m3, and so on, which I'm highlighting in blue right now, which are pairwise relatively prime. And that's in place already. And then, given A1, A2, A3, A4, and so on, we get this system, and the system uniquely determines a solution X, uniquely modulo capital M. So there are multiple X values that satisfies the system, but the difference is multiple of capital M. And then if you restrict to whole numbers less than capital M, from 0, 1, 2, 3, and so on, up to capital M minus 1, then the solution is indeed unique. That's the Chinese remainder theorem, and the unique solution looks like this. The linear combination expression, and wait a minute, haven't you seen this before? Yeah, the very same as this. Except we have x1, x2, x3, and so on. Here we use A1, A2, A3, and so on. Just a change of characters. Let's make one further observation here. This capital M and mu, which I'm highlighting in blue, all those are determined by these moduli, M1, M2, M3, and so on. That's why I'm highlighting all those in blue. Blue came from blue. This part, the blue part, have nothing to do with black part, X or A1. Remember the definition? We defined capital MK as a product of the order moduli except for the kth one. So X or A did not play any role. So that's how you get capital MK. And how about mu k? It's a multiplicative inverse of capital MK modulo small mk. Again, X and A's played no role here. They were completely determined. These were completely determined by the moduli M1, M2, M3, and so on. That's why they're highlighted in blue. So, if you have all those moduli, M1 through Mn, already in place, and then they are given as n positive integers that are pairwise relatively prime, then we can set up any system like this, and then given A1, A2, A3, and so on, we'll have unique solution X, unique modulo capital M. That's the Chinese remainder theorem. But in section 5, we take an opposite viewpoint. Instead of starting from this system, we start from an arbitrary integer, and then put that arbitrary integer X into the system. Then that X, whatever integer, will be congruent to some A1, modulo M1, and it'll be congruent to some A2, modulo M2, and that X given will be congruent to some A3, modulo M3, and so on. So X will determine A1, A2, A3, and so on. We can do backward as well. But then again, can this go back and forth, back and forth? That's a bit of a problem here. This X is arbitrary integer. So arbitrary integer X will determine A1, A2, A3, and so on, modulo M1, M2, M3, and so on, which are already in place. But if you want to go back, go to the system and use the Chinese remainder theorem, and you can get X. Is this X same as the original X? The answer is in general no. They're not the same. They're same modulo capital M. They may differ, but difference is a multiple of capital M. Again, by Chinese remainder theorem. But then again, if we restrict ourselves to whole numbers less than capital M, 0, 1, 2, 3, and so on, up to capital M minus 1, then the correspondence is 1 to 1. So you can go back and forth, back and forth. In general, if you start from any integer, then the correspondence is not exactly 1 to 1. You can come back, but there is a difference, and the difference is multiple of capital M. So we have uniqueness modulo capital M. In any case, we got the association, and we successfully had a change of viewpoint, so that any x can be written like this using the Chinese remainder theorem, and that expression is unique modulo capital M. And then for each component, x1, x2, x3, and so on, those are unique modulo small m1, small m2, small m3. Now let's go one step further. This linear combination expression is really cumbersome, so let's have a shorthand. Let's simply express it as an n-tuple. And the first component, x1, is congruent to original x, modulo m1, and x2 is congruent to original modulo m2, and so on. That's how you can get this component. So basically, this expression is a shorthand of this, the same. That's just a definition. And then using this definition and this shorthand n-tuple expression, we can define an n-tuple vector arithmetic, modulo capital M and modulo small mi's, of course. How do you do that? We can define vector addition and scalar multiplication. So x and y are like this, x1, x2, x3, and so on, and y1, y2, y3, and so on. And x plus y can be written as the n-tuple of sums for each component. Now this x plus y is unique modulo capital M, and each component, xi plus yi, is unique modulo small mi. The proof comes from the associativity and distributivity, so it's easy, that's left to you. And you can do the same to scalar multiplication. Again, the proof is distributivity coming directly from this linear combination expression, so the detail is left to you. And finally, once again, let me make another emphasis. This congruence, the uniqueness, is modulo capital M for entire vector expression, and for each component, congruent modulo M1, M2, M3, and so on. So if we restrict ourselves to whole numbers less than capital M, then you really have uniqueness. What we are going to do next is to get some really humongous M1, M2, M3, and so on, so that even more humongous capital M, so that this whole numbers, set of all whole numbers less than capital M, pretty much covers all the interesting whole numbers that we want to think of. Anything beyond those are out of our consideration. We're going to do that so that we can apply this idea into modern computation theory, but they'll have to wait. Let us solidify our understanding through an example problem. So let's have an exercise on this vector arithmetic, addition, and scalar multiplication. Here's an example. We're going to take the moduli M1, M2, M3, and M4 as 99, 98, 97, and 95, respectively. And please check if you have pairwise relatively prime? The answer is, of course, yes. You can check. I'll leave that to you. And x is 123,684, and y is 413,456. Our textbook gave me those numbers. And then x plus y modulo m1, m2, m3, and so on. We can always add them up and then put that into this. But that's actually cheating. And we want to practice this modular vector arithmetic. So let's express x as an n-tuple and y as an n-tuple through modular arithmetic like this. So how did you get 33, 8, 9, and 89? Those are all remainders. 1, 2, 3, 6, 8, 4 divided by 99 and remainder 33. This x divided by 98, then remainder 8. This x divided by 97, I don't care about the quotient, the remainder is 9. So this one, mod 95 and remainder 89. And likewise, you can get the remainders for this y with respect to 99, 98, 97, 95 with these remainders. Cumbersome computation, so I just use Mathematica for that. And then we can apply the modular vector arithmetic. Just add each component. 33 plus 32 is 65, good. 8 plus 92 is 100, but 100 exceeds 98. So we can bring it down to 2, modular 98. 9 plus 42 is 51, and then 89 plus 16 is 105. That exceeds 95. So we can bring it down to 10, modular 95. Okay, that's what we did, blue and green. Okay, so that's vector arithmetic, vector addition. And now, from here, let's retrieve our x plus y values. Does it fit with the previous computation? That can be a bit cumbersome, but we can do that. Let's see, capital M1, capital M2, capital M3, and capital M4 are like these. Cumbersome computation, but for machine, it's no big deal. Just multiply all those moduli except for the first, except for the second, except for the third, and so on. And then even worse is the multiplicative inverse computation. If you have to do this manually, then you'll have to follow that you create an algorithm that leads to Bezout's linear combination expression of the GCD being 1. And then that's how you get the multiplicative inverse. For human, that's really a big pain in the rear end, but for machine, it's no big deal. So we get all those. And then we can use all those, put everything back into this linear combination expression. Previously, you got 65 to 5110. So 65 to 5110 with capital M times mu in place. If you do your computation, you get this, and then you can bring it down to 537,140 modular capital M, which is 99 times 98 times 97 times 95. In the end, this is what you get, and that fits the traditional computation. Now, why would anybody do this kind of modular vector arithmetic while you can easily do this traditional computation? That's going to be answered in the next section, 5.3. For now, we'll have to do it here. So we used Chinese remainder theorem to define those modular vectors and went through some modular vector arithmetic, some addition, and we didn't do scalar multiplication, but that's left to you.